My name is Sam Marshall. I work in Central Office, Chemical Laboratory, Construction Materials Division, and my innovation is determination of aluminum oxide in high friction surface treatment. I'll explain a little bit about it. High friction surface treatment is a localized treatment that is used for skid control. One of the main minerals in high friction surface treatment is a material called bauxite. It contains a lot of aluminum oxide. I've come up with a method that currently there is no method around right now that can determine that amount of aluminum oxide in high friction surface treatment. So it's kind of an industry standard at this moment. So one thing about bauxite is it doesn't dissolve in acid, so it's very hard to test. They use bauxite because it's very durable, and you need the durability on that type of pavement for friction control. So the material is going to hold up for the application. So one of the things that I've done is I've came up with a way of determining it by analytical procedure and instrumental method, and I'll kind of go through it. One thing I do is you take a known weight of the sample and you put it in what's called lithium metaborate, which is a fusing agent. Okay, and what that'll do is I'll encapsulate the sample, and then I'll fuse the sample in if you want to get the camera, in a 1,000 degrees C muffle furnace. It'll fuse. And what'll it become? It'll become a fused bead like this. But usually it's a little more hot. And what you'll do is you'll drop that fused bead in a dilute nitric acid solution. And the reason you use nitric acid is because metals are stable in nitric. They won't precipitate out, they'll stay in solution. So from there, I will transfer the sample to a volumetric flask. So I have a known weight to start off with. I fuse it, I dissolve it, and then I take a sample out of it using a pipette, 50 ml pipette. So I started with 0.2 grams to a 200 ml volumetric, and I'm taking 50 mils out, which constitutes 0.05 grams. So I know my grams when I start off with. So when I take that sample, I transfer it to a beaker. And I add an indicator to it, and what the indicator makes sure that it's acidic. From there, I will add ammonium hydroxide to it, and it'll turn it this color, yellow. That knows that it's basic. And what happens if you see this precipitate? This is what I'm looking for. What precipitates out is silica, aluminum, iron, phosphorus, and titanium, right? And that's one of the those are the main minerals that are in bauxite. So from there I'll filter it, isolate it. As you can tell, you can see it's a hydroxide, so it's a little bit like jelly. It looks like jelly. So once I've filtered all that out, I will transfer that filter paper to a platinum crucible, and I'll ignite it in a muffle furnace, 1,000 degrees C. As you can tell, it's pretty hot. From there, it becomes aluminum, it becomes an oxide, essentially. The hydroxide burns off, it becomes an oxide. So what we have here is we have a combination of aluminum, iron, silica, phosphorus, and titanium here. And this is what it looks like after. So once I've done that, I take this weight of this crucible, and then I compare that weight to the original sample weight, which was 0.05, and I get a percent, what they call a percent recovery. So say I have a percent recovery of 100%. I had 0.05 grams in that crucible, and I had started off with 0.05 grams. I have 100% of aluminum, iron, phosphorus, titanium, and silica. From there, I transfer it to an inductively coupled plasma emission spectrometer. This is, once the sample is in solution, I can use this emission spectrometer to determine silica, aluminum, iron, phosphorus, and titanium, because those are minor elements in bauxite. And I have calibration lines that are bracketed that will differentiate how much is in there. The reason that I don't use aluminum oxide when I fuse the sample and put it in solution is because I don't have a high aluminum oxide standard to bracket. So if I analyze it, I can't get a true result. So that's why I use this emission spectrometer to get silica, iron, phosphorus, and titanium, and I subtract that off, and the difference is aluminum oxide.